Okay, in this video, we're going to discuss here the definition of what a logarithm is. I'm going to answer the question, well, what is a logarithm? What's it for? And the main exercises that we're going to look at is going to be switching from what we call log form to exponential form. Now, before we get to those examples, we're going to look at a lot of definitions and a lot of things about logarithms here that we need to know. Now, a logarithm, the definition is kind of hard to explain here because it more looks like just algebra than anything. Kind of know something before we get started, and this is kind of why I have the shade. What a logarithm is really going to be for is later on, it's going to help me find unknown exponents. Okay, so if I have an exponent that's unknown and I don't really know how to solve for that exponent, a logarithm is going to help me do that. Now, let's look at some things here. Before we talk about really what a logarithm is, um, we need to look at here sort of how we switch it to an exponential form, because that's really the definition. So if I have a logarithm, so logarithm is abbreviated with obviously here log, and then here I have base b, and I have x equals y is equivalent to, and then this is basically exponential form, b to the y equals x. Okay, now this will be really a simple thing once you learn it, but it is very, 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 very fundamental. And so when I go from this to this here, what I'm actually doing is I'm actually switching the form of the equation. So actually switching the form of the equation is what the definition of a logarithm is. Now, notice the relationship here between this equation and this equation. They are the same equation. They mean the same thing because it says one is equivalent to another. It's kind of like when we were talking about linear equations, we could have different forms of a line. We could have slope-intercept form, we could have standard form, we could have point-slope form. They all look different, yet they represented the same line, and that's the idea here, is they are equivalent to each other even though they look different. Now, the way I switch this and apply this definition, and you might have noticed the pattern here, is I take this power right here, or this base, excuse me. Okay, so notice the base appears right here. And I raise it to this power, and it is equal to this number. Okay, so to kind of dissect this, I can take b, and notice this b here, it's below the logarithm because that's because it's a subscript. It's sort of the opposite of like an exponent. You know, an exponent would be like right here. Well, logarithm has what's called a base here. That's why we name it with b. So if I take this b, or this base, and raise it to now y, instead of a number, it becomes an exponent, then it will be equal to the logarithm, or what I'm taking the log of. Okay, so that's how I go to this. All right, there again, let me kind of put it back in the right order here. This is my base, this is my logarithm, and this is my exponent. So I take that base and raise to this power is equal to that number. And that's what this says right here. Now, let's kind of break the parts of a logarithm down here. Now, when we look at the different parts, we have different names for them. Now, even though y is not written as some subscript or a superscript, it's not written as an exponent, it's written like a regular number's written. What it represents is an exponent. Okay, and this is why we said that logarithms are ultimately going to help me find unknown exponents. So really, y is an exponent, even though it's not written in an exponential form. It's plain old y. It's that little bitty y and raised up a little bit on your paper. Still written as a regular number, but yet it represents an exponent. Okay, now log here stands for log. Now, the b part, again, is called the base. Okay, so even though it is a little bitty, and it's written sort of below the line, it represents the base. So remember, the base is something I'm going to raise to a power, and ultimately it's going to be this power right here, that y power. Now, x is what I call the logarithm. Even though it's not written out here, log, okay, I'm taking the log of it, so that becomes what's called the logarithm. Now, here again, the base, I'm going to take it, and I'm going to raise it to the y power because the y is the exponent, and that should be equal to the logarithm x. So what we're looking at here is this is logarithmic form, and this is what we call exponential form. And that's what our lesson is about here. It's really going to be simple once you catch on to this. But we're going to switch log form to exponential form. Okay, so let's actually look at that, and we're going to look at it two different ways. Okay, and let's go back to that definition here. So if I have, say, log of base b of x equals y, okay, or we can write it backwards, which will be the same thing. Okay, so you kind of have to look at these both ways. Okay, so what this means here is I can take the b, or the base, and raise it to this power, and it's equal to this number. So we get b to the y equals x. And so, guys, when we look at a logarithm, this is what automatically pops into my head. Okay, and it's going to seem, well, this is so easy. Why are we making a big deal of this? Because later on, this is going to carry on through almost every lesson that we do in logarithms. Is going to relate back to this definition right here, and you're going to have to recall to do that. So I take this number, raise it to this power, and equals this number. Now, over here, this is just backwards there. Okay, so all we're doing here is just going to write it backwards, that we're going to say that b to the y, so this number raised to this power, is equal to x. So it's the same thing. It was just written backwards. Now let's look at some actual examples of doing this. Okay, so let's notice these actually have some numbers in them. And so notice the 3 here is the base, and y is actually an exponent, even though it's not written as an exponent. And then the 7 is the logarithm. So here I can take the number 3, okay, the base, and raise it to the y power, and this should be equal to 7. Okay, now notice what we're doing here is we're changing forms. We're not trying to figure out what y is yet. Okay, we will eventually. Again, we're just trying to change forms. Now, let's look at the next one here. And so this one's backwards. So notice that we're going to start with the base. So the base b raised to this power should equal this number. There again, when I look at this, the way that I read this, or when I look at this, is my eyes look at this number first, this number second, and this number third. I really don't read it left to right. So we get b raised to the third power equals 64. There again, we're not trying to solve for what b is. Then you can probably figure out that that would be 4. But there again, that's not what we're trying to do. We're trying to just change the form of it here. Now, the last one, let's take a look. So we've got the base here is 5. And so we're going to take 5 and raise it to the second power. So that's this number raised to this power should equal this number. So 5 to the second power should equal x. Again, I'm not trying to solve anything. I know that would be 25. But all I'm trying to do is just put something in exponential form here. So again, this is called log form, and this one's called exponential form. Now, let's look at some other things that we're going to have to consider here, and that's what we call a common log and a natural log. Okay, notice on all these, on these logarithms, they always had a base right there. Okay, this one was b, down here, this one was 5. Okay, now what you can see, and this is actually what you have on your calculator, is called a common log. So a common log is the word log, but it's written without a base. Okay, so understand 5 is the logarithm. the base is left off. Okay, so this base right here that we don't see, I'm going to do it this way to kind of, let's put a little box right here. It's sort of left off right there. Well, it's an understood base of 10. Okay, and so that's what I have to remember about what's called a common log, is it's an understood base of 10. And this is actually the logarithm button that is on your calculator. Okay, it's called the common log button. Now, natural logs, you find a lot of these, they call them natural logs because they occur in nature. Looks like this. Instead of log, it's ln for natural log, and I know that's kind of backwards there. I think it's it's another language that kind of came up with this, and so in other languages you have adjectives and nouns, and they're kind of switched, different from what we do in English. Now, on a natural log, what you have, let's say we're trying to find the natural log of 5. Of course, you have a natural log button on your calculator also. Okay. Now, the thing again about a natural log is the base is not given, but instead it's understood. So the understood base of a natural log is the number e. Okay, and e is an actual number. It's come up with this guy whose name was Euler, which is spelled like this. Okay, so that's why we call it e. We named it after him, and it's sort of an irrational number like pi. So what you have, and there's a poster in the back of our room. It's a green poster by the cabinet, and you kind of take a look at it when you think about it. But e is an irrational number, and it's equal to about 2.7. Kind of like pi is approximately 3.14. Well, e is approximately 2.7 there. And so all a natural logarithm is basically like this. It's a log with a base of 2.7. Now, let's look at some of these examples here with natural logs and common logs. Okay, so let's change these to exponential form. So let's notice on these, all these logarithms, none of them have a base. So what's the base? Well, if I don't have a base, then what we're looking at is a common log, and so it has an understood base of 10. And so to switch this to exponential form, remember we're going to take the base right here, which is missing, and we're going to raise it to this power, and it's going to be equal to this number. So this would be the understood base of 10 raised to the second power should be equal to 100, and that makes sense because 10 squared is 100. Now the next one there again, the understood base is 10. So this would just say 10 to the 7th power equals 2x. And now finally the last one's going to make sense here because we don't have any variables. Again, the understood base is 10. So this would say 10 to the 4th equals 10,000. And that makes sense because 10 to the 4th is 10,000. Now let's look at some natural logs. So my natural log here, again, it's a logarithm. It's just a different logarithm. It has a different base. And that base is that irrational number e. So even though we don't see it written right here, there is a base that is understood of that irrational number e. So this one would basically say e raised to the x power equals 5. And on my next one, it would say e squared is approximately 7.3. And if you actually punch this in your calculator, you have an e button. Just trying to think of where it was. You have to hit your second key on the natural log key to get the e button. Now, it's actually e squared is about 7.3. And now finally, we've got another base e there. It's a natural log, so e to the first power is approximately 2.7. And that's what we said earlier, that e is approximately 2.7. Now, I'm going to recap this video, and I know I'm probably boring you with this, but this is so fundamentally important here that we understand the definition of a logarithm. The definition of a logarithm here says if I have log base b of x equals y, that this b raised to that y power is equal to x. So I can't emphasize enough, when we look at a logarithm, especially a single logarithm, that when I see this, that this is automatically pops into my head, almost to the effect like this. When I say 6 times 4, we automatically say 24. And so when I see this, I automatically think in terms like that.